All right, folks. All right, let's get started today. We'll do a little recap of assignment 4. I didn't keep track of every interesting thing that I saw, but one of the most was this. So, how many people discovered that anybody could edit a Piazza post? How many use that as a weapon to try to get people to sign their adversarial key? Yeah, there's a lot of edits going on. And then the other trick that people used is after they were discovered or whatever, they would then switch the note or the question or whatever to private. So it's just to us, the instructors. So I have all of these posts with insane histories. The really interesting thing that I saw, so was it true that if you made a follow-up post to a post that nobody else could edit it? Yes. Yeah, so you saw how you as a class evolved defense mechanisms in the face of a forum where anyone can edit a question. You would say, look in the comments for this, and then the follow-up discussion would have your actual keys and everything that you posted. Let's see, other cool thing that I hadn't seen before was people taking videos of themselves going, like the weird, I mean not weird, but the interesting thing was seeing people try to submit both their real and their adversarial to get, prove that they're trustworthy by giving you their adversarial. I thought that was really interesting. Let's see. Oh, this other great post. So I saw this, and I think I've redacted all the names of all the people here, because I can see your names, in case you didn't know that. Cool. So this was, oh, I can't remember. I didn't take a screenshot of the top. This was somebody pretending that, oh, I didn't do that completely.
Okay, someone trying to be
anyways, they created a key by fake key by me for posting it that I was signing people's keys. And the really funny thing is that I don't know if this was the case, but you all a lot of you chose to post anonymously when you were actually being truthful. But then everyone else doesn't believe what you're saying because you're posting anonymously and they're not associating with your name. Particularly in this case, somebody calls about oh, I feel a lot safer if the post was made by the instructor instead of an anonymous person with, quote, his. And then you have anonymous people commenting to anonymous people following up. So these could have all been the same person. Oh, this one's good. Yeah. Notice how all the comments here are anonymous, even the one who was like, yeah, I saw that. This is 100% me. I actually don't know if it's the same person or if it was a coordinated team of people commenting on it anonymously. But yeah, so that's super interesting because, of course, if you had gone to my website, you can see that this is not my public key. So this is the hash of my public key. It's on the website. You could have imported it and checked that. Unfortunately, I don't have the grades yet. I'm still importing all of your crazy submissions, so hopefully later today, definitely by Thursday, I can go over the distribution of scamming people. Does anybody else want to share what they learned about this assignment? Yeah.
I don't know, something funny. I guess you can create random users in Piazza. Just make, as long as it's an ASU email, you can just make a new user and you can match that to your name.
Oh, I should have brought up, I don't want to go on Piazza because I see a view that you can't see, but maybe for Thursday, I'll try to get the number of posts that we had throughout the year. You can see that it spiked, and I bet our user count spiked too. Yeah, in the back.
I noticed in Piazza, someone had posts that were set to verified by the instructor, and I severely doubt that someone ever even one more time.
Yeah, good question. I don't know. I haven't seen those posts. It's very hard to find this because I had to go back through the history of all these posts to see what was actually going on.
Just figure out why that does that too. Because if you're a top commenter in the entire Piazza class, the top 5 people, their posts or comments will automatically be verified.
Oh,
At least that's how it's set up right now.
Yeah.
So you can verify a post that you thought helped students, but then actually it can be edited, so someone could have used that to their advantage and posted their ads.
Yeah, for sure. That definitely could have happened. I don't know that it did. We were pretty careful about not endorsing any of the answers on those crazy find my key posts. Yeah.
I found that interestingly, the approach that seemed to work best for me was actually relying on ASU's email system. Because if it didn't matter if you signed the wrong key, if you sent it to the ASU, or if you know, or sorry, you have to sign the right key, but if you send it to the email of the person whose name is in the box, it'll only get there if it's a real ASU email address.
Okay.
It's validated by ASU.
I see. So using like the Gmail autocomplete feature to verify identities, I thought that was clever. Is there a way to change that though? Like is that old? Yeah, so people are nodding their heads, so maybe it wasn't a great way to verify. But maybe seemed like a good place. Yeah.
So I just have a general question.
Sure.
If our key expires on like today or maybe next week, can it still be gradable?
Yeah, for sure. Yeah, the expiry of the keys doesn't matter at all. Because I'm just pulling all the data down into one key room so I can see all the signatures from everybody, and then I know who is adversarial, not adversarial. And then I can count up how many signatures you got both ways. Cool. Did anybody discover, or maybe you didn't discover, so I can disclose some of the adversarial tricks that people used, was you could send somebody a GBG file that had multiple keys in it. Right? Some people are shaking their heads, right? So I know this happened in the past. I don't know if it happened this year where somebody created a fake CSE 365 Fall 19 key that had a different fingerprint, and they would append. So because you could change your user ID of your adversarial key to your name, and then after that was done, you would lose all the signatures that you had before. So now the course signature doesn't exist. So what people would do is create a fake course key, sign their own key with it, and then ship both keys to somebody. So if you weren't actually checking that this fingerprint exactly matches the one on the server, then you would get scammed into signing something. Yeah.
Did your server require the adversary key to remain signed by your server?
No, just the fingerprints. I don't really care about the signatures. Are just for you to know what keys are valid, right? So if you change your user ID and then drop that signature, everyone else, nobody else should ever sign that key because it's not signed by the server. Yeah. Yeah.
One good question. So when the server, when you submitted your public key and it said you had to be set valid signature,
Yeah.
that system already checked those signatures you have up there.
No. Yes, it checks that those are valid in the course. That's both real and adversarial keys. Because otherwise, then you could easily just submit to test which ones are adversarial or real keys, right? So yes, I have to limit the amount of information I give you to not ruin the game. Let's see. Anybody use key servers? This was the surprising thing that didn't come up. So nobody used the GBG key servers, so they're a network of systems. I think they're in one of those docs I linked to. Sometimes the course finds these key servers, so people, it says you can upload your public key to the key server so that other people can just download it so you don't have to email each other keys. I think the first year that I did this, people created weaponized Python scripts where it would actually work to, like, it was a Python script that would check that another key was valid, except for the person that created that Python script. It would work for them, and so they could trick other people that way. Let's see, 1 year, did anybody create a certificate authority? Or have some kind of group trust system? Yeah, what did you do?
We had a big Google Doc. Everyone had to submit, and then it would be added to the Google Doc.
Did anybody scam that Google Doc?
Please say no.
This happened to the certificate authority. So the certificate authority 2 years ago, I think it was 2 or 3 years ago, they decided they were going to have like a two-phase commit. So your key had to be verified by two different, like the two leaders, and then they would add you to this Google Doc. But one person figured out, like, tricked one of them, so they weren't following their own protocols, got their adversarial name added to the certificate authority, and scammed like the 20 or 30 people that was on that list. Yeah, so you'll find out soon if you're. Any other interesting things you learned or tricks? This was definitely, yeah, please.
I didn't pull this off because I didn't think about it later, but was the backend written in such a way that we couldn't post our adversarial key again to get it signed after we change the UID?
No, you wouldn't. You couldn't. It checks. So this is why short answer is no. So A, the adverse. Let's see. Yeah, that's why it's like a two-phase thing. Like you create your own key and you upload it, and that's why we store that and generate you an adversarial key. And at that point, we won't sign anything from you or anything.
Okay. Thank you.
Anything else? Yeah.
I saw people posting their key ID on their iSearch profile as a way to verify.
Oh, cool. Could you also change your name though? On the iSearch profile?
Well, the problem is you can change your name on the iSearch profile, but you have to submit a request to ASU to do it. It's not something where you can just directly
Illegally change their name.
That's pretty cool. Yeah, that's interesting. Yeah, I didn't know that. So this, using like a trusted source of information, this iCourse, or what is it called? iSearch, right, where you all have profiles on. So using that to post your key ID so that people can verify it, yeah, that's a cool idea. Yeah.
I guess similarly, I use the ASU class roster for this class to verify names. It's on the ASU app.
But you can see the course roster.
Yeah.
I didn't know that.
Yeah, it's on the ASU app.
I didn't think that was supposed to be possible.
Yeah, I didn't know that.
Okay, so yeah, stick bowling, yeah, that's interesting. So, yeah.
I think the ASU app can store their password in plain text as well.
We can talk to them about that. Wait, what that is? Yeah, that sounds like that. That's good to know. Okay, cool. Anything else? Yeah.
I haven't been doing, but I figured like it would be possible to trick somebody with the iSearch by like posting a fake implementation of it, but then just like having the first part be iSearch.asu and then extend the rest of it to like whatever the rest of your
So like, yeah, make a phishing domain, that would be interesting. 1 year somebody tricked, like, or not tricked, but got their friend's permission that wasn't in the course. So they changed their adversarial user ID to be that, like, a person who wasn't in the course, but who was actually an ASU student and everything. And then with that other trick of having a fake CSE 365 fall 19 key, trick people to sign it because it was from a real, and the person agreed to let them use their ASU account. So it came from a real ASU account, like it was a real person, it just wasn't a person in the class. Max, do you remember anything from your year that were good?
I think the certificate authority stuff was my year. That was
Certificate authority? Yeah. That was interesting. Cool. All right, now we're gonna shift gears a bit. Oh, did anybody find an easy way to distinguish between the two? That's right, that's the other thing, yeah.
Also, I mean, the email, you don't get to choose adversarial name. So if the email matches, real name, matches the name, you can be pretty sure that it's not the generated adversarial.
Right, so yeah, the email was one thing to key on. 1 year, I think a group collected and shared everybody's adversarial and real keys, and they're able to find there's some difference in the exact, like this key, whatever, I don't even know if it's a real screenshot or if it's fake, but this RSA 4096, so this is a type of public key, private key. Like I think the adversarial keys were using like DSA for some reason, and I couldn't fix it to make them be exactly the same for some reason. So there were weird differences between the adversarial keys and the normal keys that I know some people just said, like I'm never going to sign anything that has this this specific type of key. Anyways, lots of ways to approach this. Cool. All right, now we can all trust each other again. Ha 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 ha. All right, so now on to network security. So now we've kind of got, the goal here is we're going to be learning and talking about different, how networks actually work, specifically through the lens of how we can attack and exploit them. So we're going to get kind of a crash course on how two different machines talk to each other on the broad internet, and then specifically we're going to be looking at all these layers and thinking, okay, what are the security implications of doing this thing? So it's important that we have we can cover things like firewalls and intrusion detection systems, all this kind of stuff, which we'll talk about towards the end. But to actually understand how those systems work, you need a good, solid understanding of how these protocols work. Because without that, we're just talking kind of in the abstract. And this is kind of an interesting problem, right? So you have this problem of how is your laptop that is out right now, how is that talking to, let's say, google.com, right? How does your data actually get from here to there? And how can you have a conversation with a remote system that you know nothing about? Right? It's kind of almost something that we take for granted, but it happens literally all the time. So we'll look at the protocols that actually make this up. So it kind of starts out with the IP, the Internet Protocol Suite. It's a set of protocols that are used to transport data. It's also called the TCP/IP stack suite, whatever, all kinds of things. Very nice. It's based on kind of abstraction and encapsulation, although these layers kind of break down, and we'll see that. So, for instance, does Google need to know that you're on a Wi-Fi network in order to talk to you? Or a 4G or an LTE network, right? Those are all different ways. So you think, I don't know, can anybody see, is there a Wi-Fi router in this room somewhere?
Yes.
Yeah, you all pointed in different directions, so. There's one the exact same thing right over here. So I don't know where it is, but I guess maybe, or maybe that thing there. That thing. The microphone maybe? Anyways, right, so your information has to get somehow from your laptop to that Wi-Fi router that's somewhere in here, right? And then from there it needs to go from ASU's network all the way to Google's network, and then it has to come all the way back. So the nice thing about how this is designed is Google doesn't care if you're on a Wi-Fi network or a wired network or whatever, you can still talk to each other. Kind of built up in these terms of layers. So there's this physical layer about how does data get from like physically across the air medium of whatever 802.11 whatever that it's talking here for wireless. For LTE there's a different protocol, right? There's all these different ways of how to actually talk from one machine to the other. I don't really know exactly how all these things work. You can go look it up and find it. And then we kind of build up from there to say, okay, we have a way to talk from one end to the other. Then how do these two ends of a link actually talk to each other? So how does your laptop say, hey, I have some data I want to send to the Wi-Fi router, and how does your Wi-Fi router know it's your laptop and not somebody else's laptop or somebody else's phone? So it needs some ways to disambiguate there. All the way up to how do we then talk to Google, and how does our data get there, to then all the way up to the applications that we want to actually talk about. So HTTP, I think we should be pretty familiar with that protocol, right? Web pages, all that kind of stuff. What's SMTP for? Mail. DNS. Domain name service. It exists so that we don't have to remember 32-bit numbers when we're trying to access websites. Right? We want to go to google.com, not whatever their IP address is. NFS, the network file system, so a way to have file systems. So there's all these different applications. This is an important thing to remember when you're discussing networking with somebody, to make yourself seem like you know what you're talking about. If you just call everything the web or the internet, like a lot of people kind of mix these two. We say, I got it on the web, but the web is just one application that runs on the whole IP stack. There are many others. Speaking of SMTP, did anybody spoof any emails to, or attempt to spoof emails to scam people? Some people. So there's a couple hands, 3 hands, 4 hands. The problem is getting that reply back. Yeah. So you could spoof an email to somebody from whatever email address you want, but of course, getting that reply back is difficult. Okay. So we're gonna first start at the beginning. So we need to know how to talk to each other, right? So the thing I really like to think about is in terms of the postal service, although maybe this is getting more and more out of date. Has everyone sent and or received a letter through a postal system? Some of you not. Have you seen a letter? Don't they still teach you that in grade school? I remember that in elementary school, like what the things go, where to. Ooh, okay. So how does the post office know how to get your letter from one place to another?
The destination address.
So a destination address, so what does that consist of? Postal code, zip code, the name of the person, the town, the city, the state, apartment number, address, right? The specific address on the street, right? So all of this information is an attempt to uniquely identify the location of a person. Apparently, I don't know if this is still the case, but it used to be that as long as you got the city roughly correct, I mean not roughly, but correct, then the postmaster there would be the one to deliver your letter. And so you could say things like the red barn that's like 2 streets down from the doctor or whatever, and as long as the postmaster knew how to deliver that, they could actually figure out who you were talking about. But can you do something like that with computers? Do we say, I want to send this packet to, I don't know, to San Jose, California? We can specify a street. No, we need some way to reference each other, right? And so we need to know, okay, if I want to send a letter, we can think about it at this point, on the internet to another machine, I need to know what that destination is, of where that letter is supposed to go. And this is the concept of the IP address. So hosts have one or more IP addresses, usually on their network interface. So network interface is, if you have a desktop wired machine where you connect your Ethernet, it's your Wi-Fi card on your laptop, all that fun stuff. So one of the fundamental things of an IP address is it's 32 bits. Do we usually write out, so we know we can interpret 32 bits as, let's say, a hexadecimal number. Do we think about hexadecimal numbers or IP addresses as hexadecimal numbers? No. Do we think about them as just integers?
Close.
Like base 10 integers?
Yeah.
Yes. Or sorry, what's that? Base 10? Yeah, base 10. So you say I want to talk to 2,964.
Well, there's periods. It's like 192 point.
Yeah, there's a different way of interpreting them. So, but actually, so this is an interesting point. A lot of systems you can actually reference an IP address just by the number. So if you have a firewall or a system that's blocking you from accessing a local host, like 127.0.0.1, you may be able to get through by putting the integer value of the number. So this, what we call dotted decimal notation, should be very similar to how you're used to thinking about IP addresses, and maybe you've seen this before. What does this represent? So I said it's the same thing. So what does this represent?
It's the decimal representation of each 8 bits.
Yeah, so every byte, so the, okay. So it's 32 bits, right? So 32 bits, we have the first 8 bits, the second 8 bits, third, and the fourth. So what's the range of each of these? And so we'll put a dot in between them.
0 to 255.
Yeah, so we know they're 8 bits, so 0 to 255 for each of these, right? And so you can easily take this number and turn it back into a 32-bit integer, right? By taking this value, turning it into the bits here, here, and here, and then interpret it as a number. Cool. So this is a nice way to think about And so this gives us how many different IP addresses?
Did 255 to the power.
Yeah. 2 to the 32, how much is that? 4 billion? Right? Seems like a lot, right? Yeah, 4 billion, that's a big number. Is it a small number?
Small.
Saying a lot of. It seems like a big number. It is a big number. 4 billion is a lot. If I was going to give you $4 billion, would you say no? That's not enough money. It's a small number. No, you'd say it's a lot of dollars. I would like to have that, please. I don't have $4 billion to give you. Sorry. So the question, though, is to how to essentially portion up these 32 bits to all the different entities that want them. So it used to be you had fixed different classes of IP addresses. So one organization would get a chunk of IP address space, and the way that this is done is we got to talk about. Okay, cool. I'll do this now. Cool. Okay. So, key thing about the IP address is kind of like in the example of a letter, right? We had a postal code and a city which told roughly how do I get my packet to where it needs to go, or how do I get my letter to where it needs to go, and then the other information specifies specifically within that region of how do I deliver that. So similar things about the internet. So one of the very important concepts, so what does an internet mean? How's that different than an intranet?
A mean?
What was that?
A mean? Internet mean?
No, mean. What does it mean? What is the meaning of it? Yeah.
An internet is like computers connected outside of like an organization, and an intranet is like an internal collection of computers not connected to anyone outside of the organization.
Yeah, so you can actually think of it in both ways, right? So it kind of encompasses both. So the intranet, so inside, intra, I believe. So a network of computers that's all controlled by one entity or organization. And then, so let's say we have ASU very nicely here as one network that is controlled, right? ASU can decide exactly how information goes and travels inside. But now when ASU wants to send data to Google, which has its own intranet, right? We need protocols of how that's going to happen because there may be other places along the way, like whoever our service provider is. So basically what we need is, in some sense, some notion of how do I get from this IP address, how do I know where this should go? Or what, let's say, another way to phrase this is what part of this is the postal code and what part is specific to that destination. So it used to be you had fixed sizes, so you'd say, okay, the first, man, I wish I had the sizes here. So you'd say the first, what is a class A? I think it's 11 bits or something. So the first 11 bits specifies the organization. So anybody that has the same 11 bits goes to google.com, and then they figure out what the rest of the bits mean internally. Okay. It turns out that's a very inefficient way to distribute IP addresses because you're giving some people huge ranges and other people very small ranges. So there was this idea of CIDR, classless interdomain routing, which allows you to specify this boundary between, and we'll get into this more in a bit, to specify the network ID and the host ID, so where this boundary is. So if you've seen an IP address of the form, hard to come up with numbers. Let's say 128.125.0.10. So a slash, what would this be? A slash 16 would mean that the cutoff is here, in between the second and third octet. So the first 16 bytes determine the network that it goes to. and the last 16 determine the host. And similarly, so 128.125.0.10/24 would say that the network host is the first 24 bits, and then the exact host is the last bits. And so we've actually, I think, technically run out of IPv4 addresses. We'll talk about why that's not a huge issue, or why it's not as big of a deal as it should be, but we can kind of ignore that for now. Okay, so this is how to read IP addresses. We'll get into exactly how CIDR is used and how this split between the net ID and the host ID is actually used to deliver packets. So we're going to start out kind of actually in the middle of the diagram. So we're going to start out with the internet protocol, so at the IP level. So essentially you can think of it as the glue of the internet. It really is the way in which data moves throughout the network. One of the really cool things about the internet is it doesn't really matter how a specific organization, so ASU could decide, hey, we don't want to use IP internally, we're going to use something completely different. But to get packets where they need to go, as long as they can talk IP to other networks, your packets can go where they need to go. Very important to understand the different capabilities that each of these networking protocols provide at each of these layers. So IP is connectionless, unreliable, best effort datagram delivery service. So what this means is that you say, hey, I want to send an IP packet to this other machine. You know what that other machine's IP address is through another mechanism. And the network will do what it can, but it means that your packet it's not guaranteed to get there. It's not guaranteed that what gets there is exactly what you sent, integrity. It's not guaranteeing the order, which means that if you send packet A and then packet B, the other side may receive it B then A. There's no guarantee in what order they receive things. Bandwidth isn't guaranteed, so you're not guaranteed a certain chunk of data. But very cool, it allows you to exchange data between any two nodes. So as long as they have IP addresses, like if they both have an IP address, then you can exchange data between any two hosts on the internet. So this is why this is such a key core principle. So let's look at this first. So is that a good thing? So I talked about connectionless, unreliable, best effort. Is that good? No, why not? You would like the internet to be reliable, right? So you'd like it to be the fact that when you send something, something actually gets there, right? Have you ever sent somebody like a text message that they didn't receive? Think about, you're a human communicating. Imagine trying to make computers talk to each other when packets just magically disappear. Thoughts?
Alternatively, if you did guarantee the arrival and the integrity of packets, that puts a lot of overhead on the system, which might make it inaccessible. So it's trade-offs, really.
Yeah, so you're gonna have to do something. Like we'll see later exactly how these mechanisms work, but you have to do extra work in order to make sure, hey, did you get my message, right? So you need to make sure there has to be more communication overhead. The other thing to think about is look at where in the stack the IP layer is, right? So you have the internet protocol layer, which allows us to send data between any two hosts on the internet, right? We didn't talk about what data we're trying to send or any specific applications. So you want something that's kind of at this layer to be essentially support almost all protocols, right? Or any possible protocol that you could think of. So is there protocols or is there an application where you actually don't care if you lose data or lose a packet? Yeah?
Thinking like Skype and video calls.
So Skype and video calls?
So because you send so many packets at any given time, right? And then if you miss a packet for a specific pixel or something, no one's going to notice it. So
Right, so an audio call, or you can think of like an audio call, right? If you drop a packet that's maybe a quarter of a second of audio, do you want to delay the other person's communications until you find that data and then keep talking, right? Then you'd have huge latencies whenever there was a dropped packet. Yeah.
Another one would be like an online game.
How so?
Because the same reason there's so much being sent, if you had a guarantee, it would really slow it down, and it's supposed to be quick.
Yeah, so an online game, right? So you have a bunch of clients connecting to a central server, and the server is storing the state of the game and pushing out the state of the game to every client. So if one of the packets was lost, who cares? You're going to get another update in another second or whatever, which will update your game state, right? So yeah, so it's interesting to think about that looking at this seems insane. Like, why would you want a protocol that is unreliable, is best effort, has no integrity? So why no integrity? Yeah.
I mean, just like the post office, once you send it out, it's out of your hands, you know?
Sure, so okay, so then like the post office, you send it out and whatever, maybe a bird rips it in half or takes a bite out of it, and some letters are gone from your message. Yeah.
So when it's like routing through, it's passing through a whole bunch of different networks that isn't necessarily the person you're sending it to, and anyone can intercept it along the way and do something like change the bits or something.
Yeah, so this is all the reasons why it's not, but is this what you want?
No, it's not what you want.
It's not how you want it? But why do they do it like this? So one of the important things to learn is to look at a system, and this happens a lot even in your professional career. You're going to come to some application that was written over the last like 5 to 10 years, and you're going to read the code and you're going to be like, why in the world are they doing it this way? This is the dumbest possible way to do this thing. And then after you talk to people, you realize what crazy constraints they were under that you don't understand, which is why the code looks the way it does. So one of the things to always ask yourself is like, well, why aren't they doing this here? Like, why isn't integrity important here? Yeah.
Well, I mean, if you want it to be important, you could always write something on top of it that makes it important. But then that way it's support both situations where it is needed.
Yeah, so one of the ways is, again, this creating a broad protocol, right? That you're not enforcing anything, that upper level protocols can do if they want. Yeah.
It's like there's so many packets being sent around the world to guarantee integrity for everything. The massive overhead.
So this is another thing to think about is what was the context? What year was it when they were creating these? I believe late 70s, early 80s. I don't have the number on this, but so you think about integrity there, doing like what we talked about. So you could actually send with every message, or well, okay, that's a good question. So if you assume, okay, we'll use some kind of hash function, but you look at the hash functions back then, adding that to every single message that was being sent could actually be significant CPU overhead. Plus, you have this problem of what's your actual threat model? So integrity kind of what or from whom? So let's say to every packet you append a hash of the message that you're sending. Does that guarantee integrity? No, why not?
Both of them could be corrupted along the way, because the hash can be corrupted.
Not just corrupted, but if you're going to guarantee me integrity, that means that Eve, who's listening to that packets and can modify and change those packets as they're going across, could change the message, calculate their own hash of the message, put it there, and send it across, right? So we need not only integrity, but we need who generated that IP address, right? So then we have the problem of public-private keys, and you kind of get into all of this craziness of if you want to guarantee some sort of integrity. Cool. Okay, let's look at an actual IP packet. So this is from one of the other things I try to urge people is don't be afraid to look into standards. So this is RFC 791. An RFC is a request for comments. It's the Internet Engineering Task Force puts out or people write up these and submit them as kind of standards, different kinds of standards. So if you want to learn what is everything I need to know about the IP protocol, you could go read this document and you will be moderate expert at IP by the time you're done. Okay, so how do we read this diagram? Yeah.
From left to right, 'cause I think it's bits.
Left to right bits. Yeah, so this is data that's being sent, right? So why don't we just send the data? Why isn't this just like, here's the data to send? Yeah.
The model operates in layers, right? So it needs to be able to strip away or add, stuff at specific points.
We need stuff, right? Just like a letter. You can't just write a letter and just throw it into a mailbox and expect somebody to magically know where it's supposed to go. So if we think of it from that perspective, what stuff do we need? So this is the other thing. Before we even look at it, we should think, what has to be on here? What are we looking for? Yeah.
IP address or something.
So the destination IP address, right? Who are we trying to talk to? Makes sense. Just like a letter, we need the destination address on there. What else? Yeah.
The actual content.
The content. The content has to be somewhere. What else?
Who sent it?
Who sent it? Is that strictly necessary?
Only if you want something back.
Only if you want something back, but oftentimes, why are we sending a message if we don't expect something in return, right? So, just like on an actual letter as well, or I guess technically an envelope, whatever, you put the all the sender's information so that you can get a response back, right? So we would assume that we have the content, the destination IP address, the source IP address. The other thing to think about is how big can the content be? Yeah.
Maybe as big as the size of the connection, or it could be whatever size you want, depending on how you send it.
Yeah, okay, so yeah, it could be, we don't want to specify that every message has to be 1,000 bytes or whatever, right? So we probably also need, what's the size of the message? Because somebody needs to be able to read how much are you trying to send. So we can see that, okay, cool. All right, so the first 4 bits are going to be the version number. Why is that important? So we're going to spend a little bit of time thinking through these things for like, why is the first 4 bits that are sent the version number? Yeah. Yeah, because it tells you how to parse the rest of it, right? Is it IPv4? Is it IPv6? This is actually a very good design principle for a lot of things. So this good, like a REST API that you're talking to might have the version number in it, so that in the URL, so that you can know what version you're talking to. Specifically here, if it's IPv6 or IPv4, that defines how you're going to parse the entire rest of the packet, right? And how you interpret those bytes, because it may depend on which one. So that's why this has to be essentially the first 4 bytes, or first 4 bits that you receive, sorry. Okay, then some other stuff. We finally get to the total length of the packet. So this tells us the entire length of everything, I believe including the content and the header and the packet. We have something we didn't talk about. We have an identifier. We'll get, I don't know if we'll get into exactly how this works. Some flags, so we can set different flags to mean different kinds of things. Oh, this is an interesting one. So time to live. So this is, the basic idea is, okay, let's say so should we assume that can we assume that the networks are perfect?
No.
Why not? Yeah, for many reasons, right? You could say humans are developing it. You could say, fundamentally, on the internet, our data is being sent to some other machines that we don't control, right? So if I said, okay, I want to send a packet, I want to send a letter to google.com, or whatever google.com's IP address is, right? So I send it out, and then how do I know that it's, so one of the cases that could happen is you get into a weird networking loop, where one system gives it to a next one, and that one gives it to a third system, which gives it back to the first one, which gives it to the second one, and the third one. And then you have just this message that continually exists in the system that's being passed around forever, right? This is actually things that can happen. It's very easy to mess up systems, so they do this. So there's a built-in mechanism to not have that happen, where essentially this time to live value starts at some certain value, and then every step of the way it gets decremented, and when it's 0, it gets dropped on the floor. So this prevents kind of infinite routing loops that can happen. Interesting bit here is the protocol. So this is information in the IP address header that specifies what the higher level protocol is, which is one of these weird breaking of abstraction layers. And then, interesting enough, there's actually so we said it doesn't guarantee integrity, and yet inside this header there's a checksum which is used to see if, which is used to validate the rest of it. We'll go back to that in a second. Source IP address. So double check, does this make sense in this diagram? How big is an IP address?
32 bits.
32 bits. We have exactly 32 bits here. For the source IP, the destination IP, any optional heading, optional headers, padding, and then finding the data. So one thing to ask is, why is there this header checksum? What is a checksum? It's a crappy fast hash output, I would say. It's definitely not a cryptographic hash function, but it can detect if, let's say, a bit was flipped somewhere along the way. And so you could at least see if there's any kinds of those transmission errors. Yeah, anything else?
Yeah, question.
Yep.
So each row of this, what is this? Is each one a packet, or is the whole thing a packet?
The entire thing is a packet.
Okay.
From all the way to start to the end. The way to think about this is this is just a stream of bits, right?
So it's way more than 32 bits, the packet.
Yes, we're just splitting up the 32 bits for
Okay.
ease of viewing in some sense, right? So you get all these bits and it just keeps coming, and then the other side has to then parse those bits back into what they mean and then act upon them. Question? Yes?
Is the checksum like a handing code?
I don't remember. You'll have to look at that. CRC, I think it's a CRC 30, no, it'd be CRC 16. It's a 16-bit checksum. But yeah, it's very bad at, I think if you flip a bit and then flip another bit the other way, then the checksums will be the same. It's very easily prone to problems, but it's at least good enough to know that, like, hey, a bit flipped, maybe I should drop this packet, but there's nothing that guarantees that it won't mess with the packet. More questions? Okay. Now, important thing to understand from here, we're not going to go through this all again, is, all right. Okay, let's go back here. All right, so again, remember, this is just some data that's being sent from one side to the other. So when, so A, is there anything in here about encrypting the data that we're sending?
No.
No. So this is essentially the way, actually probably the best analogy to think about packets sent through the network is in terms of a postcard. So what's the difference between like a postcard and a letter and an envelope? Yeah, an envelope technically is sealed, right? And you can even do, I mean, you could put a wax seal on it to see if anybody's broken it or opened it or whatever, right? Whereas an envelope, or sorry, a postcard, right? Everybody can read the contents. Every postal worker that touches that can read the contents of that note, right? So very similarly here, the data can all be read. We'll go back to this in a bit because I want to. Cool. Okay. So the question is, all right, we're going to go to drawing time. There we go. Okay, so we have, we'll build up a little network here. We have a host. This will be a switch we'll get to in a second. Okay, so we we are here. We have Google. And then, okay, so we want to send a packet to Google, or sorry. I need another person. Somebody say a name. Sarah. There we go, cool. Okay. All right. So, we want to, all right, there we go, cool. So, Sarah has an IP address. Google has an IP address. And, I don't like this us, but. Okay, we all have IP addresses. So I'm going to send a message to Sarah. So just on this diagram, right? What's the difference between Sarah and Google? Yeah, so we think about the circles with the X's in them as switches or something that's going to take our packet from one place to the other. We'll get exactly into how this works. We see that we need to essentially transfer, go across two of them to get to Google, but Sarah's on the same network essentially that we're on. The question is, how do we know that? So I'm going to draw a beautiful dashed line around our network. So us and Sarah, we're on the same network. How do we actually know that?
Would be your IP, the first 16 of the IP address.
Yeah, so let's look at something. We'll call Sarah 10.0.0.3. Will be 10.0.0.2. And Google will be 10.0.10.1. Is that possible? No. Depends on how I want to do this. Okay. Okay, cool. This is good. All right. So, when we configure our network, right, for us, we're 10.0.0.2, but that's not the only piece of information I need to know to be able to send packets, right? I need to know what is our local network versus everyone else, right? I need to know this dotted line distinction. I need to know, is Google on the same network as us or not? And how I do that is through basically what we talked about before, the net ID, host ID. Other ways to think about this, oh no. I think it's fine. It's done grading, so. Yeah, okay. Cool, I'll go to the server. Oh, sorry, this is really small, isn't it? Okay. So if we look at this, oh, this is going to be confusing, great. Okay. So on the website, Ethernet 0, so this is the Ethernet adapter, its IP address is 172.31.6.250. So that's the IP address. Now it needs to know, how do I determine local versus remote? So it comes down to that CIDR thing we talked about. So here, there are many different ways to look at this. One is this net mask. So this says, okay, so this is my IP address. 172.31.6.250. And my net mask is 255.255.240.0. So what's 255 in binary?
Just saying ones.
All ones? Yeah, so we can see. Can I zoom in with the calculator? No. Okay, so it's all ones here. So this is 1, 1, 1, 1. 8 ones here, same here, 8 ones. 240 is 111, so all that's the first 4 bits. 1, 2, 3, 4, and then 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So essentially it says everything that's a 1 is what we use to determine the local host. So so what we can do is take any IP address and it with this value. If it matches and it's all 1s, then we know exactly where to send it. So this would be a slash, what is this? This is a 16 and 4 / 20. So it's a /20 network. So this means use the first 20 bits in order to determine if an IP address is in your local or your remote IP. So then with this information, then here we can tell, okay, is 8.8.8.8, is it local? For this? How do you know? Yeah, none of the bits match, right? I mean, starting from the beginning. So, no. What about 172.31.137.20? Is this local?
What's the subnet mask?
/20. So this is what we're going with here. What is the binary of 137? 137 is 1000101. So the way we can think of this, do the first 2 octets match?
Yeah.
Yes, so the first 16 bits match. Then here, this is, we expand this out, it's 10001001. We say, do these match? Does this match this? Is it just 6? Yes, no? No. So this is not a local address. Okay. .10.20. Yes, let's see. We'll do 10 here. We see that the first 4 bits are all 0, which is the same as the original one, so yes, it is local, right? So, let's say that my IP address here is a /24, which means my net host boundary is here in between all those octets. So to make it easier, since we're not splitting in the middle of an octet. So, with this information now, so my IP address, my net mask that defines my local network is 10.0.02/24. So, is Sarah in my local network? Is Google in my local network? No. See, that's the only piece of information I need is my IP address and my network. Then I can decide if something's in my local network or not. Now, if Sarah's in my local network, then I can send the packet using direct delivery through the physical network. So let's look at this. Cool. And so essentially, and this is kind of building up, so we had what we looked at before, our IP address header, some IP data. That's going to be encapsulated into a link layer, into some frame header and frame data, which is usually Ethernet in most cases, I think almost all. So this means we can deliver it directly, essentially. So we know somebody's on our local network. It means that we can speak a link layer protocol and talk to them directly and send it to them. Which means that here, the other way, this is another way to look at the subnetwork. So 111.10.20. So this means that is our subnet. So we can see that we have one machine that's 111.10.20.121 with some. So this will be the physical, the link layer address or the MAC address, which is what we'll see in a second. And we want to send a packet from .121 to .14. And so we need to create this packet, but we need to know how to create this packet. So, and that gets into then Ethernet. So Ethernet is a much simpler format. So first we need to know, all right, cool. Okay, let me switch these. Okay, cool. So Ethernet is at the link layer, so let's go back to the link layer. So we can see here from our stack, we have IP, so we need to send that IP packet on our local network using the link layer, which is Ethernet. We'll go here. This uses 48 bits for addresses. So if you've seen this kind of, everybody's seen a MAC address before that has this kind of colon separated values. Right? Each of these is 0 to 255 represented as hex. So we have destination addresses, so 48 bits, source addresses, 48 bits. Then we'll have the specific type of message, and data can be between a max of 1500 bytes and a minimum of 46 bytes. And then we have, again, a CRC check. So let's look into this really quickly. So this is actually a much simpler file format because there's not much, we don't have to have all this metadata about who we're sending it to and all these options. We just have the destination MAC address we're trying to send to, the source MAC address, specifically what type of message, of Ethernet message we're sending, and then the data, and then followed by a CRC32. So in case the data is an IP datagram, which is the case we're interested in right now, the type would be set to that, and the data would be the IP datagram. There are various types of messages here, which we'll get into in 1 second. But we've hit a roadblock, a bit of a roadblock here. So I lied a bit, or maybe I lied. I said before that we're 111.10.20.121, and we want to send a message to 111.10.20.14. So we have our source IP address, we know their destination IP address, and we know the data we want to send. But what else, what don't we know? Say again? Yeah, we don't know any of these numbers, or we know ours, right? We can know our MAC address, but we don't know what their physical link layer address is, right? And so we need some way of mapping, hey, we're trying to talk to IP address 111.10.20.14. What's their MAC address? So you have this interesting mix where these layers have to blend, where you want to know what MAC address has this specific IP address so that you can talk to them. And that is a great, and this protocol, yeah, please.
Sorry, let's space out for a second, but what's the importance of MAC addresses?
So we need some way to talk, it's at a different layer. So the link layer here is the Ethernet layer. So we're essentially operating at the internet layer. We know the IP address we want to talk to. We don't know their MAC address necessarily, and so we need to figure that out. Based on their IP address, can we ask for their MAC address?
Like, why do we need a MAC address? Because aren't IPs like, does every machine on a local network, or like on a network get assigned a different IP?
Possibly, but you can configure, you can have multiple IP addresses on one NIC, on one MAC address. So you could, it's not directly a one-to-one mapping. I think, well, going back the other way is a huge pain if you ever have that in your network, where multiple machines have the same IP address with different MAC addresses. But this allows you more flexibility because so you have a network of 1,000 machines, right? So they all have different IP addresses. Maybe you hard code that. Somebody gets a new machine with a new MAC address because that MAC address is tied to that physical card. Now you have to update all 999 machines with what's this new MAC address for this IP address. When the network has this flexible protocol to map, it has a way to ask, hey, who has the MAC address for this IP address? Yeah? MAC address is 100% changeable. So you can, theoretically, if you were on some system like a Wi-Fi network that restricted you a limited amount of access time to that network, if you don't log in with the username and password, the only thing that it has to identify you is your MAC address. So by changing your MAC address, you can make it think that you're different devices every time you talk to it. Similar things could work if you bought internet, let's say on your iPhone, and that is tied to your MAC address. Then if you turn off your iPhone and change the MAC address of your laptop to be your phone's MAC address, the router would have no way of knowing that it's a new device. Mostly no way of knowing. Yeah, and actually I want to say the iPhone either has an option to randomize your MAC address when you're talking to public Wi-Fi hotspots, because that's also a way you can be tracked by your MAC address when you talk to different Wi-Fi hotspots. I believe so. So yes, fundamentally there's nothing stopping you from changing it. The network needs a way to keep up and to catch up that you now have changed your MAC address. Cool. So we need a protocol to translate between the two. And it seems kind of crazy, but we're going to essentially use Ethernet to do this translation. And this actually is one of the really cool key ways of how you can impersonate another machine on the network through manipulating our the address resolution protocol. So the key idea, essentially you can think of it as a protocol where you blast out a message to everyone saying, hey, who has this, what's the MAC address associated with this IP address? That message goes to everyone, and then the person who has that MAC address, or that IP address responds. So essentially, let's say we have some network, we have host A and host B, and this is actually something you can look at. You can inspect your ARP cache on your local machine. So ARP-A is a way to show all of the mapping between IP addresses and MAC addresses in your network. You can run this on your machine. So host A wants to ping host B. So essentially it has some data that it wants to send to 192.168.1.10. How does it know that this is on the local network? Yeah, it looks at the subnet mask, figures out the network ID versus the host ID, says yes, this is. Now, host A will send a broadcast Ethernet. So this is output of TCP dump of this. So we can see on the left here, this is the source MAC address, and it's going out to, and again, so you need some kind of essentially value that says, hey, this message is for everyone, right? Everyone on this network. So that's what the all Fs is. So I don't know who the specific MAC address that should receive this, right? Because I'm trying to ask everyone on the network, hey, who has 192.168.1.10? So it broadcasts it out to everyone. Who has 192.168.1.10? Tell 192.168.1.100. Every machine on this network will get this packet. Only the machine that has that IP address will respond back. And we'll now, so the request goes to everyone. Now host B will respond with a reply. That will say, now at this point it has everything that it needs. It knows the destination MAC address, 08.146.07.04.83, because of the original request packet, so it knows exactly who to send it to. And it says, our reply, hey, 192.168.1.10 is at 013.1D98B8. So this goes to host A. Host A receives this and then updates its ARP table. And of course, because you don't want to do this for every packet that you sent, this is cached locally, so you can see on both host B. So now both host B and host A both have this mapping between IP address and MAC address. Yeah.
So can you change who's going to receive the information and say, tell this IP address?
Change which information? What do you want to change?
So it says tell this IP address. Does that mean you can make the other computers all tell a different computer other than you?
we'll talk about kind of trust issues here when we talk about spoofing and hijacking these kinds of communications. So, yeah, fundamentally, there's nothing. So, A, if you look, there's nothing that links those two requests and response together, right? There's nothing that says that host B actually has that IP address except for the fact that they respond to this request. So host C could have responded and said, yeah, I'm over here. And host B may never, so host, anyways, you can play games like that. Yeah, there's fundamentally nothing stopping you from doing that. But this happens all the time on your networks, every time you're connecting to a system, yeah.
So I get, I get the mapping from IP to MAC address, but how come, I still don't understand why we need it, because on the open internet, if they went on your network, all you need is an IP address.
Correct.
So, and if an IP address uniquely identifies a host, can't you just use that instead of having to ask for a MAC address?
You need essentially you need some way of getting data from one host to another, right? So that is at a high level, that's IP, right? So the high level idea of how you get data from one IP address to another, but the actual mechanisms of how data moves from one host to the other on a single local network is not clear. So that's what the Ethernet has to do. So you need something to do that.
Okay.
Right, and the idea was they decoupled IP addresses from link addresses in some sense. So, but you need to be able to kind of stitch them back, and that's why you need this protocol to translate between them. And then once you have this, so once you have the ARP, once you have all the ARP information, then you can easily just send the packet that you wanted to send. So this was this last final IP packet that was sent from 192.168.1.10 to 192.168.1.100. So once we have that information, we have everything we need to send it, and then everything just happens. So this is all on a local network. When we have direct delivery, we'll look at attacks on this, and then we'll look at what happens when we need to pass data across multiple hops.